Mass spectrometers are common instruments used in many chemical and physics laboratories. They work by shattering compounds as the sample enters what's called the source, forming ions that represent a type of fingerprint for the particular compounds in the sample mixture. The various ions formed by this process are separated and measured in terms of their mass-to-charge ratio by the mass analyzer. Then the intensity of the various beams formed is measured by the detector. Let's watch as the mass spectrometer system is being started up. After bringing the system pressure down to the ultra-high vacuum region, the source is turned on in preparation for the sample introduction. The source of the electrons for the electron beam is a tungsten filament, the same commonly found in old-style household incandescent bulbs. An electrical current passes through the filament, which heats it to an orange-yellow glow. The electrons are formed into a beam by applying electrostatic and magnetic forces between the filament and what's known as an electron trap on the other side of the source. The job of the electron beam is to ionize the sample molecules by fracturing them and removing one or more electrons. This source operates at positive 10,000 volts, which effectively makes it an ion accelerator or gun. As soon as a sample molecule is ionized, it's accelerated out of the source and on to the next stage. Let's follow a sample into the instrument. The high electrical potential of the source has no effect as we float into the source area, but it won't be long before the molecules hit the electron beam, are fragmented, and converted into a positive ionic state. The sample ions move out of the source quickly and pass through a series of electrically charged lenses that focus them into a beam. The series of lenses form a tight circular beam shape, similar to how optical lenses in a camera focus light. As the round beam proceeds past the lenses, it passes through a very thin vertical slit, which blocks most of the beam and reforms it into a ribbon shape as it exits the slit. The ribbon beam achieves high resolution, or the ability to separate fine details in the spectral pattern or fingerprint for the sample. When the gas nears the curve, a large electromagnet deflects the ions by differing amounts, depending on their mass-to-charge ratio. Once into the curve, the single beam, which up to this point has consisted of all types of fragments and ions, begins to split off into many different beams, sort of like a prism effect with light. The curvature of each individual beam depends on the mass-to-charge ratio of the beam component and the magnetic field strength. Precise control of the magnetic field results in fixed curvature of the ion beam of interest based on mass-to-charge ratio of that species. Beams heavier than the beam of interest hit the outer curve of the flight tube radius, and beams lighter than the beam of interest hit the inner curve of the flight tube radius. Both beams hit what look like fishbone stops along the inner and outer radius of the tube, where they're neutralized and then pumped out of the system. Beams that are very close in mass-to-charge ratio of the targeted radius or radius of interest make it through the curve and head on to the Faraday detector. As the magnet power increases, each beam of interest reaches the fixed radius so that it can enter the Faraday detector. Beams on either side are blocked by the slit plate. At the end of the flight tube are receivers or detectors called Faraday cups that collect the charged particles. When the sample ions strike the surface of the cup, they produce small electrical currents in the cup and are neutralized and pumped away. Based on the high voltage potential applied to the source and the strength of the magnetic field, the relative mass of the ionized atoms can be calculated to very high accuracy. The quantity of each atomic or molecular species can then be determined based on the total pressure of the gas at the source and the output of the amplified Faraday cup currents. It's been observed by facility startup engineers that whoever operates and maintains these instruments comes closer to controlling the whole facility than the central control room does. This comment wasn't based on the premise that the instruments or analysts make the process decisions, but that they are the most highly sophisticated instruments controlled by some of the most highly trained personnel in the facility. Together, they provide nearly all chemical information required by the process. If they are not operational, no process decision can be made. Support of these instruments are a good career choice for chemists, physicists, and even biologists, whether that support is providing technical oversight for the instruments, maintaining and repairing the instruments, or operating the instruments.